All right, welcome back, Math 20-1 students. So today we are looking at the last lesson in this chapter. So in our last lesson, remember that we learned about geometric series. So basically when we have remember a geometric sequence is a pattern of numbers that are determined by multiplying the former term by a ratio to get the latter term, and then you can go on we'll talk about that today, whether it's infinite or not. You can keep going with that, right, to create a pattern of numbers. And so the geometric series is looking at the sum of those numbers that form that pattern in the sequence. And so today we're going to extend a little bit on the idea of a geometric series by looking at something called an infinite geometric series. So to start out with, again, we're going to look at this investigation. So as I've mentioned in the past, you can go ahead and pause the video and try and complete this yourself because you have all the knowledge you need to work through this on your own. And it's going to be most beneficial if you try it on your own anyways. So if you pause the video and you've come back, I'll quickly go through kind of the general idea of it. So in this diagram, we start with a square piece of paper. And then we do the following set of steps. So the first thing we're going to do is, if we think about this larger square here, we're going to divide that in half. So that's this line right here. And then we're going to shade in one of the halves. So we're going to shade in this half here. Okay. Then, because we're already working on this side because that's how I had to draw it. But of course, if you did this separately on your own diagram, it doesn't matter which half you shade. Then you're going to go into the unshaded half here, and you're going to draw a line to divide it in half. So of course, initially this would be just one full side. We cut it in half across this way, and then we want to shade in one of those halves. Okay, and then it says repeat the previous set at least 6 more times. So now we're going to basically look at this square here. We divide it in half and we can shade in one of these. Okay, so that's one. And then we can, I'm just going to go really not super tidy here. Cut that one in half, shade it in. So that's the second time. Cut this one in half. That's a third time. Cut this one in half. That's a fourth time. Cut this one in half. That's a fifth time. Cut this one in half. And that's a sixth time. Okay, so we've done that 6 times and shaded in the remaining section there. So it says write a sequence of terms indicating the area of each newly shaded region as a fraction of the entire page and list the first 5 terms. So T1 was this first section that we shaded, and so as a fraction of the entire page we had basically just cut it in half, so the fraction would be 1/2. Then T2 is where we took the second half and we cut that in half. So this out of the whole page is 1/4, right? We can fit 4 of these squares into the page. So 1/4. T3 would be where we take the next quarter and we divide that in half. So this would be the next section. And we can fit 1, 2, 3, 4, 5, 6, 7, 8 into the page. So that's going to be 1/8. T4. Now hopefully you can see what the pattern is here, right? So we have a half, a quarter, an eighth. What's the relationship between these numbers? Do we need to keep using the diagram to visualize whether or not, or what fraction of the page it would be? Hopefully you can see the pattern here. We have the denominator being doubled each time. If you want, we can have a look though, because this was an eighth. So the next one we would be looking at is this eighth was divided in half. So we're looking at this section. How many of those would fit into the page? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is one shaded square out of 16. And so we see that the pattern holds where the denominator is doubling. So I'm not even going to try and count for T5, I'm just going to assume that it's double this, and it's going to be 1/32. Okay. So then we're asked, is the sequence arithmetic, geometric, or neither? So basically, if we look at getting from one term to the next, are we adding a value, or like adding or subtracting, I guess, because sometimes we have a negative value that we're adding, or are we multiplying? Well, if we wanted to get from a half to a quarter, we would have to subtract a quarter. But if we subtract a quarter from a quarter, we should be at 0, not 1/8. So we know it can't be arithmetric. So what about geometric? If we, like we said, if we multiply the bottom by 2, then we're getting each successive term. And so that would make this geometric because you're multiplying each one by, basically by 2. Wait, let me think about that. 1/2. If we do a half times by 1/2, then we get 1/4 times by 1/2 equals 1/8. So yeah, we can say that our just trying to think here. Half times a half. Yeah, times, I think I might have put this wrong in my filled in notes because I had divided, which would be 2/4. Oh, no, because I solved for the R value. Sorry, guys, spaced out there for a second. I was trying to figure out what I did in the previous one. So yeah, here I'm just saying, like, I know that I have to multiply it by a half. If you guys wanted to just solve for the R value, remember that you can do the second term divided by the first, or any one of these successive terms divided by the former. So basically what I did in the filled in notes, if you're wondering what I did there, I solved for R because remember it's going to be the second term divided by the first. So it's going to be basically 1/4 divided by a half, which is the same. Remember that when you divide fractions, it's the same as multiplying by the reciprocal. So it's the same as doing 1/4 times by the reciprocal of this, which would be, instead of 1/2, it's 2/1. And so when we multiply that out, 2 times 1 is 2, 4 times 1 is 4. And so we end up with 2/4, which is, of course, 1/2 as our R value. And that's what we said here, right, is that we would have to take the first term, multiply it by an R value of a half to get the second one, multiply that by an R value of a half to get the third one, and so on. Okay. So the next thing here is, ignoring physical limitations, could this sequence continue indefinitely? So in other words, would this be an infinite sequence? So of course, like, we have physical limitations of the page, which, you know, I was starting to feel even just drawing those 6 terms. But if we ignored that, could you just keep multiplying fractions by a half? Yes, you could, right? Like, you could keep on going infinitely and multiply by a half, because what's going to happen is these fractions are going to get smaller and smaller and smaller, right? Like 1/32 is quite a bit smaller than a half. But remember that whenever you have any number multiplied by any other number that's not 0, it's not going to make 0. So we're not going to actually get to 0 by multiplying these by a half. We're just going to get infinitely smaller and smaller fractions, which is kind of mind-bending, but that's the way it is. Okay, so I'm not going to write it out, but we would say yes, you could form an infinite sequence because you could continue to multiply the terms by 1/2. Okay, the last section, we're going to break out our calculators here, and it says, using a graphing calculator, input the function y equals a half to the power of x. So when you're inputting, this is our first use of the graphing function in Math 20-1. So what you want to do to get to this page is hit y equals up here. Okay, and then you want to input your function. So when you're doing that, I would put it in exactly the same as here. So we want to have close bracket and then 1 divided by 2. Close the bracket and it's raised to the power of, so that's this button here. X is our exponent. You always want to make sure you use this button here to push for the x. So there we have to the exponent of x. So now I have my function entered in. what I want to do on this one, so you can either go to the graph, but for this specific one, what we want to do is get to the table of values that will be generated for this function. Sorry guys, I'm having a hard time fitting everything into the screen here. Okay, so we want to get to the table, and so basically what we're going to do is hit second function graph, and you can see that it says table up above there. And so now this is going to generate a list of values for us. Okay, and so what it asks us is, using the table of values from the calculator, what happens to the value of the function, which is always the y value, as x gets larger and larger. Okay, so we have x is increasing, and what's happening to y? Well, y starts at 4, 2, 1, half, quarter, eighth, 16th, right? So we're going smaller and smaller and smaller, down to like 0.0039. So basically we can say that y is getting closer to 0. Okay, again, I'm not going to write this all out because it's in the filled in notes. And can the value of the function ever equal 0? This is basically what I explained before. No, it cannot, because no number multiplied by another non-zero number can ever equal 0 if it's being multiplied. Okay. And again, you can find that in the filled in notes, the written out answer for you. Okay, so let's get into this idea of infinite geometric series. I'm just going to grab some papers. I don't like that feeling when you're getting too close to writing straight on the counter. Okay, so a convergent series is a series with an infinite number of terms, okay, in which the sequence of the partial sums approaches a fixed value. So all this is saying is we have an infinite number of terms, right, in a convergent series, and if you start adding those numbers together, as you add more and more terms, you're going to find that you're getting closer and closer to one specific number. So this is always going to happen when your R value is between -1 and 1. So it's important to be aware of that, because you are going to have to be able to identify if something is a convergent or a divergent series. So knowing that convergent series have an R value between -1 and 1 is going to help you to be able to identify that. The other thing will be if you can check and see that the sum is approaching this set value. So for example, if we look at the series that we just got off of this table, right? 4, 2, 1, 0.5, 0.25. If we add the first 5 terms together, so if we find the sum of 1, 2, 3, 4, 5, these ones, we get 7.75. Then if we add the first 7 terms, we get 7.9375. First 11 terms, 7.9961. First 15 terms, 7.9998. And so what is the value that we seem to be closing in on? Well, it would be 8, right? So we're getting closer and closer to 8 as we add together all these terms. But because the terms are getting smaller and smaller and smaller, we're just going to kind of like keep on approaching this value. Okay, so in math, we basically end up saying that the sum of that series is 8 because we're getting so close to it with all these smaller and smaller terms. So the really important thing to pull away here is when you have a convergent series, your R value, you can identify that it's convergent because it's going to have an R value between -1 and 1. So basically it's going to be a decimal, right? Your R value will be like a negative or a positive decimal value. And so if you have like this infinite number of terms, you're going to approach a value. And so we can essentially say that there is a sum to those terms. Okay, that's a set value. So in this case, that was 8. Now, the other kind of series we can look at is called a divergent series. And hopefully you guys recognize these words. Converge always means you're coming together. Divergent always means you're spreading apart. Okay, and so with a divergent series, you can probably guess from that explanation, right? If convergent means you're coming together to eventually converge on this number 8, divergent is the opposite. It's where your sums keep getting further and further apart. So a divergent series is a series with an infinite number of terms. So both of these are infinite geometric series. But in this divergent series, the sequence of partial sums does not approach a fixed value. Okay, so in a divergent series, we see a different type of R value. It's going to be greater than 1 or less than -1. So basically, the R value is going to be a whole number, not a decimal. Or actually, that's a lie. It could be a decimal, but it's going to be like a decimal greater than 1 or less than -1. So you could have like 1.25, 1.5, things like that. But the whole point is that when you multiply, the next number in the term is going to increase instead of becoming smaller like this. Or it's going to become increasingly negative, but it's not going to become closer to the 0 the way it does for the convergent series. So, for instance, if you consider this series 4, 8, 16, 32, we have, it's clearly being multiplied by 2, right? So R is greater than 1 in this case. And so if you were to add together the first two terms, 4 and 8, we get 12. If you add the first three terms, 4, 8, and 16, we get 28. First four terms, 60. First five terms, 124. And so you can see what's happening with the sum is that they're getting further and further apart, right? Here they were getting closer and closer to 8. Here we have 12, 28, 60, 124. They're getting infinitely further apart from each other, if anything, not closer to one number. So as the number of terms increases, the sum of this series continues to grow, and it does not approach a fixed value. Okay, so that's really important. It does not approach a fixed value. And so therefore the sum of these series cannot be calculated, and that's probably even more important for you to remember, because we're going to look at this formula here, which is the formula for the sum of an infinite geometric series where R is between -1 and 1. And that is really important for you to know. So you cannot use this formula unless your R value is between -1 and 1. Okay, so important. Because it has to be a convergent series in order to find a sum. You can't find the sum for the divergent. Well, sorry, you can find the sum, but because they're not approaching the same number, you can't use this formula for a divergent series. Okay, so make sure that you know that. However, just keep in mind for your formula sheet that you're going to be using on your test, you can't have this written down on there. Okay, so just make sure that you have that memorized before you go into the test, and that when you see this formula, you're going to remember that. Okay, so this formula contains terms that we're already familiar with. T1, first term in the series, R being the common ratio, remember, between -1 and 1, and then here we have this other little symbol here. Remember, we've always done SN or S with the number value of the term that we're on. But in this case, we do the infinity sign because S infinity represents the sum of an infinite number of terms. Okay, so let's try some examples with these infinite series. So the first one says, determine whether each infinite geometric series converges or diverges, and then calculate the sum if it exists. So I just want to remind you guys again, because this is something I see often in tests, and it's good to practice when you're working through problems that are not on a test. Remember to pay attention to questions that are asking you to do more than one thing. Keep track of that in your brain, because lots of students miss out on marks on tests when they forget that there's a second thing you need to answer. So we have two things. Determine whether each infinite geometric series converges or diverges. So that's our first thing we need to find. And then if there's going to be a sum, then we need to calculate it. Okay, so we have two things to do. And even on a test, you can make that notation to yourself to remind you that there's two things you need to do. So in order to determine if something converges or diverges, we need to know the R value. And R is found by taking the second value, 1/5, and dividing it by the first value. So in this case, it's 1/5 divided by 1, which is just going to be 1/5, which is nice and easy. So is this value greater than 1 or less than -1 or between -1 and +1? Well, it's a fraction that is between 1 and -1. If you're not super confident in your fractions, you can always type it into your calculator really quickly to check. 1 divided by 5 is 0.2, and you know that that is between 0 and 1. So that means that we're dealing with a convergent series, and you can tell because the terms are getting smaller as well, right? So we have a convergent series, so we can calculate the sum. So we can say the sum of this like infinite series is going to be, let me just grab our formula sheet here. So sum for an infinite series is going to be t1 divided by 1 minus r. So t1 divided by 1 minus r. Okay, and so if we plug in our values here, t1 is 1, and then we're going to have 1 minus 1/5 on the bottom, okay, which is that 0.2. So we're actually going to have 1 over 0.8, and if we do that, we're going to end up with 1.25, okay? So we can say that S of our infinite values is 1.25. Okay. Oh, and sorry, we had two things to answer there. So the first thing we would say is it's convergent. And then sum is 1.25. Okay. What about this next one? 4, 8, 16. So you can probably already tell that it is diverging, right? The numbers are increasing, but we want to confirm by calculating our R value. So 8 divided by 4 gives us 2, which is a value greater than 1. And so that means that it is R is greater than 1. Sorry, I always have to think a second about those things. R is greater than 1, so divergent and no sum. Okay. All right, another example here, last one. Assume that each shaded square represents 1/4 of the area of the larger square bordering 2 of its adjacent sides, and that the shading continues indefinitely in the indicated manner. Oops, I need to take that out. Okay, so basically we have a shaded square. It's 1/4 of the size of the square that is contained by 2 of its sides, right? So this shaded square has a side here and a side there, so it's 1/4 of this big square. And then here, this square is going to be 1/4 of, these are the 2 sides of the square that contains it, and so it's going to be 1/4 of this whole area, right? So we want to write down what would be the series of terms that would represent this situation. So if we want to represent this situation, we don't want to keep saying like, yes, this is 1/4 of the bigger square and this is 1/4 of the smaller square. But if we write that as a series of terms, we're just going to be writing 1/4, 1/4, 1/4. So we want to keep all of these squares in reference to the larger square. So T1, this square is 1/4, so 1 out of 4 parts of the larger square. T2, T2, this square is 1/4 of one of these quarters. So again, you can always think how many would fit into this square, right? Well, we have 1 shaded out of 1, 2, 3, 4. We would have 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We would have 16 squares in there. And then T3, now here's where you can kind of start either looking at the pattern here. What do you think is the pattern if you go from 1/4 to a 16th? You can still try and count here. So if we look at this square, it's 1 shaded, oops, jeez, getting clumsy here. So 1 shaded square out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and there's going to be 4 right, it's 16 in this one square times by, there's 3 more squares, so a total would be 16, 32, 48, 64. So it's 1/64th. And now you can hopefully really for sure see that there's a pattern. 4 times 4 is 16. 16 times 4 is 64. So the next one, T4, is going to be 64 times 4, which is 256. Okay, and of course the terms would carry on like that. So the second part of this question is how much of the total area of the largest square is shaded? So basically we're looking for what is the sum of all of these shaded parts, right? Now, because we can see that this is a converging series, we know that we can calculate the sum. So first of all, we want to calculate our R value. So we can do T2, which is 1/16th, divided by T1, which is 1/4. And I always like to just rearrange it to do my multiplication. So 1/16th divided by 1/4 is the same as multiplying it by the reciprocal, which is 4/1. And when you multiply fractions, it's super easy because you just multiply straight across. So it's going to be 4 times 1 is 4, 16 times 1 is 16, and then we can simplify. So 4 fits into 4 one time and into 16 4 times. So we can say our R value is 1/4. Okay, so now that we have our R value, we can go ahead and use our sum of an infinite series formula. So T1 over 1 minus R. T1 over 1 minus R. Our first term was 1/4 divided by 1 minus R, which is 1/4. So that's going to give us 1/4 over 1 minus 1/4 is 3/4. And 1/4 divided by 3/4 is 1/3. And yeah, that's our S value. So we could always say here that it's a convergent series. So there is a sum. Okay. All right, so that's everything. We are finished chapter 1. You guys have an assignment to work on from the textbook here. And then if you want to go ahead, the last 2 pages of this are a practice test. So the practice test is here. It's a couple pages long, so it's going to be really helpful for you guys to kind of get things figured out, and all the answers are on the last page. So that's it for chapter 1, and I will see you guys again in chapter 2. If you have any questions about the practice test, send me an email with like questions that you find to be really difficult, and if I get an email with a few different questions in it, I might post a video of the practice test. But I won't do it if you guys don't email me with like any questions that you really struggled with, because I'll assume that you found the test easy and you got all the answers right. Okay, so I will see you in chapter 2.